Okay, let's dive right into this explainer. For centuries, leaving Earth was just an impossible fantasy. Literally a myth told around campfires. But today, we're tracing the incredible journey of how humanity actually pulled it off. We're going to see exactly how we took fanciful poetry and transformed it into the explosive, hard physics needed to reach the stars. It is wild to think about how we went from ancient storytelling to calculating the precise mathematical formulas required to shoot giant metal cylinders into the freezing vacuum of space. So, how exactly did we bridge that gap? Because before we had orbital mechanics, all we really had was pure imagination. How did we cross the chasm from just dreaming about alien visitors to actually building the tools to go find them? Even without grasping the natural laws governing the universe, early humans still had this deep primal urge to explore the heavens, and they relied on these elaborate tales of ambitious heroes trying to conquer the skies with whatever tools they could conjure up in their minds.
I mean, our ancestors were completely obsessed with the sky. Think about the Greek myth of Icarus, right? Paying the ultimate price for flying too close to the sun with wax wings. Or the ancient Indian epic, the Ramayana, which detailed heroes literally ascending into the heavens. Obviously, these weren't engineering blueprints, but they were absolutely crucial. They were the first sparks of human ambition that laid the psychological groundwork for everything that was going to come next.
Now, that ambition hits a massive turning point in the Renaissance. When early stargazers finally pointed the first telescopes upward, they completely shattered the old dogmas. Suddenly, planets weren't just these glowing, untouchable deities in the sky. They were physical, mappable destinations. And as human knowledge about nature grew, those fantastical, mythological visions really started to give way to rigorous observation and a massive thirst for actual mathematical truth. Enter the scientific heavyweights. Copernicus proved Earth wasn't the center of the universe, Kepler mapped out the planetary orbits, and Newton finally unlocked the physics of gravity and motion. Actually, Newton realized this totally wild concept. He figured out that if you fire a projectile fast enough, it won't just fall back down. It will fall around the Earth, endlessly. Boom! The concept of the artificial satellite is born. Space travel wasn't magic anymore. It was just a matter of mastering these universal laws of physics. But hey, mastering those physics was tough, even for early science fiction. Take the 19th century and Jules Verne. He famously imagined shooting astronauts out of a giant lunar cannon. Which is a fun idea, sure, but scientifically, completely lethal to the crew. Real-world engineers quickly realized that to actually survive the trip and maneuver in a vacuum, a spacecraft couldn't just be a dumb bullet. It had to carry its very own explosive propulsion system.
And that brings us to a very important number. 7.9 kilometers per second. Just to wrap your head around that, traveling that fast is like crossing the entire city of London in the blink of an eye. That's the precise escape velocity required to perfectly balance centrifugal force against Earth's gravity. Without the atmosphere there to slow it down, a ship moving at that speed essentially falls around the Earth indefinitely. But getting anything that heavy to go that fast, that required a totally new kind of engine.
Now, solid gunpowder rockets, those had been around since ancient China, but they have one fatal flaw. Once you light them, that's it. You can't turn them off. To actually travel through space, engineers had to invent the liquid fuel rocket. By isolating the propellants into separate internal tanks, astronauts finally got the ability to throttle their thrust or even shut down the engines entirely, which gave them total precise control over their flight path. It is basically a marvel of controlled chaos. You have these incredibly powerful turbine pumps that force a liquid fuel and an oxidizer into a combustion chamber. And when they meet, it creates this continuous, violent chemical combustion. Because of Newton's third law of motion, blasting those high-pressure, high-speed exhaust gases out of the bottom nozzle generates the immense backward thrust you need to literally cheat gravity.
But man, the engineering trade-offs here are just brutal. For instance, liquid hydrogen is incredibly lightweight and generates massive exhaust speeds. Great, right? But keeping it condensed as a liquid requires chilling it down to a mind-numbing -253 degrees Celsius. So engineers end up having to build these massive, heavily insulated flying thermoses, constantly battling the immense weight of the tanks against the actual efficiency of the fuel.
So, figuring this out really becomes this massive chemical puzzle. Do you use something like nitric acid and hydrazine because they're compact and easy to store in smaller tanks at room temperature? Or do you look way into the future with atomic energy, using nuclear reactions to instantly superheat liquid propellant? Because at the end of the day, the ultimate goal is always the exact same: maximum exhaust speed with the absolute minimum fuel weight. Okay, so once you actually master all that explosive thrust, you could finally park artificial satellites safely above the atmosphere. We're talking past the 150-kilometer mark. If you go any lower than that, atmospheric friction just drags you right back down. But past that line, the vacuum is so thin that even meteors don't burn up. It is the perfect, silent real estate for massive space stations, forcing us to master the weird duality of living in total weightlessness while figuring out simulated rotational gravity.
And here's a fun fact. As we push further out into the solar system, the math actually throws us a bit of a bone. Escaping the moon's gravity well, for example, only requires about 1/20th of the energy it takes to leave Earth, since its gravity is just 1/6 of ours. This makes launching return vessels vastly easier, even if just surviving in that harsh, vacuumy environment makes every single physical task on the surface a grueling challenge.
But true interplanetary travel? That completely shatters our sci-fi tropes. You can't just point your nose at Mars and hit the gas in a straight line. Because both planets are constantly racing around the sun at completely different speeds, navigators basically have to thread a cosmic needle. It becomes this massive game of patience, plotting and coasting along complex elliptical trajectories, timed so perfectly that your ship and Mars arrive at the exact same point in the void at the exact same moment.
So, look at what we've accomplished. We actually did the impossible. We translated ancient campfire myths into the cold, hard mathematics of liquid combustion and elliptical orbits. But mastering the physics of spaceflight? That just opens the door to a much, much heavier question. Now that we finally have the keys to this massive clockwork universe, what, or maybe who, is waiting out there for us in the dark?
Welcome to this explainer. You know, for thousands of years, humans have looked up at the stars and just wondered what it would actually take to reach them. Well, it turns out it's not just about building a massive engine. It's really about conquering the invisible chains of physics that hold everything to the ground. Let's get into it. So let's kick things off with a massive thought experiment to establish the stakes. What exactly prevents a rocket from just launching into the sky, pointing its nose upward, and floating away forever? I mean, it sounds simple enough, right? But the reality is gravity isn't just some force acting down here on the surface. It's an invisible tether that extends way out into space. As a rocket climbs, gravity is relentlessly pulling it right back down toward the center of the Earth. To actually leave, you can't just fly up. You have to fundamentally outrun the pull of the entire planet. Here is the roadmap for today's explainer. We're going to start with the gravity problem, move on to reaching cosmic velocities, explore liquid and nuclear power, and wrap up with the multi-stage solution. All right, section 1, the gravity problem. To really wrap your head around this, picture a giant cannon placed right on top of a massive, incredibly high mountain. We're talking sitting right above the Earth's atmosphere. Now, if you fire a projectile horizontally from this peak and there was absolutely no gravity, it would just fly perfectly straight out into the void. But because of gravity, that projectile gets pulled downward, tracing an arc until it hits the ground. Make sense? Now, if you fire it faster, that arc gets wider and it travels further before hitting the Earth. So, the whole core concept of spaceflight is achieving an unimaginable horizontal speed. You want to widen that arc so much that as the projectile falls, the curve of its fall perfectly matches the curve of the Earth itself. It literally keeps falling, but the ground just keeps curving away from it. And that, my friends, is what an orbit actually is. Now, the difference between an airplane and a rocket? It is literally night and day. An airplane relies entirely on its environment. It pushes against air resistance to generate lift and stay aloft. But a rocket? It operates in the deadly emptiness of a vacuum. With absolutely no air to push against, it has to rely entirely on brute force propulsion and this continuous, relentless war against gravity. Moving right along to section 2, reaching cosmic velocities. Okay, so to actually beat that gravity, we got to cross a hard mathematical threshold, 7.9 kilometers per second. Just let that sink in for a second. 7.9 kilometers per second. That is roughly 28,000 kilometers per hour. At that speed, you could fly from New York to London in, about 10 minutes? That number is our absolutely critical first measuring stick for success in space exploration. We call this the first cosmic velocity. It's the exact speed where an object's forward momentum perfectly balances out the downward pull of gravity. So when a spacecraft hits 7.9 kilometers per second, it effectively stops falling back to the ground. It becomes an artificial satellite. It just coasts indefinitely in orbit around the Earth without needing to burn any more fuel just to stay up there. At this point, it has completely conquered the immediate fall. But hey, orbiting is really just being held captive by Earth on a slightly longer leash, right? If our ultimate goal is to leave Earth entirely, say head to the Moon or Mars, we need to hit a staggering 11.2 kilometers per second. This number is mathematically known as the second cosmic velocity, or as you've probably heard it called, escape velocity. At 11.2 kilometers per second, the spacecraft achieves so much energy that its path changes into a parabolic trajectory. It effectively snaps that invisible tether. Now, Earth's gravity will still pull on it, kind of slowing it down as it travels away, but that pull will never, ever be strong enough to drag it back. It has completely broken free from Earth's grip. And once we hit that magical 11.2 kilometers per second, it is a total game changer. We unlock the gateway to the entire solar system. Suddenly, the orbits of Mercury, Venus, all the way out to Pluto become accessible to us. We are no longer bound to our starting point. We literally become cosmic navigators, plotting courses across hundreds of millions of kilometers of empty space.
Which brings us to Section 3, liquid and nuclear power.
Now, knowing the speed we need and actually achieving it, those are two very different things. To hit those numbers, we need serious thrust. On one side, we have traditional chemical liquid fuels, the reliable workhorses of the space age. But on the other side, we have the massive, almost sci-fi potential of nuclear propulsion, which really represents the next frontier of deep space travel. Let's break down the chemistry first. Inside a liquid-fueled rocket, it's basically a highly controlled explosion. Powerful turbines pump a combustible fuel, like alcohol, along with super-chilled liquid oxygen directly into a combustion chamber. And remember, there's no air in space, so the rocket actually has to bring its own oxygen. They violently mix, ignite, and blast extremely hot exhaust out the back, which pushes the ship forward. But here is the catch. Even the absolute best chemical rockets max out at pushing a vehicle to around 4 kilometers per second. Wait, 4 kilometers per second? That's barely half of what we need just to reach orbit. So that's exactly why scientists look to the alternatives. A nuclear rocket operates on a totally different principle. Instead of burning chemicals, it uses the raw, intense heat of an atomic reaction to instantly superheat a liquid, something like hydrogen or helium. This superheated liquid expands violently into a massively pressurized gas, blasting out of the exhaust nozzle at speeds that traditional chemical rockets could only dream of. The efficiency and top speed potential here are just enormous, and it effectively reduces the fuel mass you'd need for long-haul interplanetary trips. And that leads us to our final part, Section 4, the multi-stage solution. Okay, so we have a huge problem. If chemical rockets can only hit about 4 kilometers per second, how in the world do we ever reach 11.2? Well, the ultimate enemy here is dead weight. Imagine driving your car on the highway and literally throwing the heavy, empty gas tank out the window just to go faster. That's essentially the whole concept of a multi-stage rocket. Instead of building one giant rocket that carries all its heavy, empty tanks all the way to space, the vehicle is actually several independent rockets stacked together so they can actively shed weight mid-flight. Let's see how this works in action. First, the massive bottom stage ignites, burning a truly insane amount of fuel just to fight through the thickest part of the atmosphere. But once it's empty, it doesn't drag that useless metal into space. No way. It dramatically detaches it, letting it fall right back to Earth. And at that exact second, the next stage up ignites. Because it's now pushing a much lighter payload in the thinner atmosphere or even the vacuum of space, its speed drastically multiplies. By stacking these stages, we compound the speed, finally allowing us to shatter that 11.2 kilometers per second barrier. As we wrap up this explainer, we've seen how overcoming Earth's gravity requires not just immense power, but absolutely brilliant engineering. We have to mathematically plot our escape, harness incredibly volatile chemical or nuclear reactions, and literally throw pieces of our own ship away just to reach those required cosmic velocities. But I really want to leave you with this thought. Once human ingenuity fully harnesses these forces to permanently break Earth's gravitational chains, what magnificent mysteries in the dark void are we going to conquer next? Thanks so much for joining me on this deep dive, and I'll catch you on the next one. Welcome to another explainer. Today, we're going to completely dismantle a massive misconception pop culture has been feeding us about how spaceships actually travel through the cosmos. Because if you've ever watched a sci-fi movie and just assumed that navigating the stars is basically like driving a car or flying an airplane, just point your ship in the right direction and step on the gas, well, you are in for a really fascinating surprise. So let's dive right into this. It's the most natural question in the world, right? When we want to get somewhere here on Earth, we look for the most direct route, a straight line. So why wouldn't spaceships just point their nose directly at a target planet, like Mars or Venus, fire up those thrusters, and fly straight there? It seems completely logical, but in the realm of orbital mechanics, trying to fly in a straight line isn't just difficult. Practically speaking, it's literally the worst possible way to travel. To really get why, we need to look at the huge gap between science fiction and science fact. In sci-fi, we're totally used to seeing ships with their engines burning nonstop, right? Just lighting up the dark void as they carve a perfectly straight path to whatever alien world they're heading to. But real spaceflight is completely different. The reality is all about engine shutoffs and curved coasting. In fact, real spacecraft spend the vast majority of their journey completely silent, with their engines totally turned off. You know the exact kind of artwork I'm talking about. The classic sci-fi covers showing a spaceship halfway between the Earth and the Moon, thrusters roaring, just flying as the crow flies. But that concept, and thousands of illustrations exactly like it, is fundamentally wrong. A spaceship's trajectory is almost never a straight line, and the engines absolutely do not burn for the whole trip. To fly like that, you'd need an impossible, mind-boggling amount of fuel. And this brings us to the real secret of space travel: momentum. Think about how vehicles work down here. If your car engine dies, friction with the road and air resistance slow you down until you stop. But space? Space is a vacuum. There is no air resistance, zero friction to slow you down. Because of that, a spaceship only really needs its engines to fire for a few minutes to hit its target speed. And once it hits that speed, it shuts the engines down entirely. The ship's momentum just carries it forward, potentially for millions of miles. So, real spacecraft coast silently through the void. Literally just minutes after launch, the fuel is spent or the engines are deliberately cut, and the crew, or, the robotic probe, just coasts. They let that initial violent push from the rocket do all the heavy lifting, riding that wave of momentum for months or even years. It's actually a beautifully serene reality compared to the fiery chaos we're used to seeing on screen. And it is absolutely crucial for saving the massive amounts of fuel required to leave Earth. Okay, but that brings up a really valid follow-up question. If we have all this momentum and there's no friction out there to stop us, why can't we just use that initial burst of speed to coast in a perfectly straight line directly to our destination? Why bother with curves? Well, space might be empty of air, but it is certainly not empty of influence. The invisible elephant in the room here is the sun's immense gravity. Our solar system isn't some flat, neutral playing field where you can just draw a straight line. The whole thing is entirely dominated by the sun's massive gravitational pull. Every single object in the solar system, including the Earth, which we are launching from, is already caught in that gravitational grip. We are constantly being pulled inward while moving incredibly fast sideways just to stay in orbit. So you really have to wrap your head around this staggering number. 30 kilometers per second. That is roughly the speed the Earth is moving sideways as it orbits the sun. When a spaceship launches from Earth, it already has that intense sideways momentum. To travel in a perfectly straight vertical line away from the sun towards another planet, a ship would have to burn an astronomical amount of fuel just to cancel out that 30 kilometers per second of sideways motion. Fighting the sun's gravity to force a rigid, straight path, it's a battle we simply cannot afford to fight with current rocket technology. To make this a bit more intuitive, think of a boat trying to cross a really fast-flowing river. The current is inevitably going to push that boat downstream, creating a diagonal path, right? Or think of skipping a stone across the sky. Earth's gravity instantly starts pulling it down into an arc. Out in space, it's the same deal. Spacecraft basically have to surrender to the powerful currents of celestial gravity. So, how do engineers actually navigate this crazy environment? It's essentially a highly efficient three-step dance. Step 1, burn fuel intensely but briefly to reach a very specific, highly calculated initial speed. Step 2, shut those engines off completely to conserve your resources. Step 3, coast. But remember, you're not just coasting blindly. You're coasting on a mathematically perfect curved trajectory dictated entirely by your momentum and the gravitational pull of the sun and planets. As a spaceship leaves a planet, the very act of escaping that gravity naturally creates a sweeping trajectory. You don't shoot straight up and away. As the planet's gravity weakens its hold on the ship, the path naturally bows outward. That initial arc is essentially the spaceship catching the solar system's gravitational currents. It perfectly sets the stage for the long, sweeping journey ahead. Which brings us to the strict geometry of real space flight. Let's summarize the actual rules of the road here. First off, paths are never straight. Never. Instead, spacecraft follow either elliptical paths, think of stretched out ovals, or parabolic arcs. By treating the spacecraft almost like a multi-million-dollar celestial billiard ball, engineers leverage the laws of physics to calculate these beautiful, sweeping arcs that rely entirely on momentum and gravity to get you to your destination, essentially for free. The mechanics of space dictate that the absolute most efficient path, the one that doesn't require a ship the size of a skyscraper just to hold all the fuel, is a curve. You launch, you arc outward, and you just let gravity gently bend your path through the void until it perfectly intersects with whatever target you're aiming for, whether that's Mars, Jupiter, or Pluto. But there's a massive catch to this whole curved coasting thing. Planets are moving at targets. Mars is zooming along its own orbit right now. So space navigation isn't about aiming for where a planet is today. It's all about predicting exactly where that planet will be on its own orbit months or even years from now, and then timing your own curved trajectory to cross that exact point in space at the exact same moment. Honestly, it is the ultimate game of precision timing. All of this leads us to a really profound realization that beautifully sums up today's explainer. In the practical, physical reality of space travel, the shortest line between 2 points in space is not a straight line. I mean, geometrically, sure, but realistically, fighting gravity to force a straight path costs way too much fuel and energy. The smart way, the efficient way, really the only way we can currently travel between worlds, is to surrender to the curves of the cosmos. But hey, science never stands still, does it? There are some tantalizing hints out there about the future of spaceflight. Things like atomic propulsion, which could offer such immense, continuous power that we might no longer have to rely on coasting. We might actually be able to ignore the gravitational currents, stop treating spaceships like thrown stones, and finally just fly straight. Until then, though, we travel by the elegant, invisible curves of gravity. Thanks so much for joining me for this explainer. Keep questioning what you see and keep exploring.
You know, for generations, we've all looked up at the night sky and dreamed about setting foot on worlds like Mars and Venus. But taking that sci-fi fantasy and turning it into reality? Well, that requires a massive leap in engineering and logistics. So in today's explainer, we're unpacking a brilliantly elegant concept that makes interplanetary travel an actually achievable logistical masterpiece. We're talking about the great cosmic harbors of tomorrow. So, let's just get right into it. How do we actually send a massive spaceship to Mars or Venus? I mean, when we watch rocket launches on the news, it kind of looks like a straight shot right into the void. But a journey to another planet? That requires carrying tons of life support, extremely heavy equipment, and an entire crew over hundreds of millions of kilometers. And if we try to make that massive leap directly from the surface of our planet, we basically hit a giant brick wall of physics.
The whole dilemma really boils down to this: launching directly from Earth versus launching from space. From the ground, we are fighting a colossal uphill battle against Earth's gravity. We're pushing through a thick atmosphere, battling friction literally every inch of the way. But launching from space, that offers this elegant, almost beautiful efficiency. It completely rewrites the math of space travel because it removes the absolute heaviest burdens before the long journey even begins.
To break free from Earth's gravitational grip starting from the ground, a spacecraft has to reach a staggering 11.2 kilometers per second. That is Earth's escape velocity. Think about that for a second, traveling over 11 kilometers every single second. Achieving that requires an immense, mind-boggling amount of energy, which of course means packing an astronomical amount of chemical fuel.
And this 11.2 kilometer per second requirement, it creates a massive physical barrier that we call the gravity roadblock. It is a brutal balancing act. Because you need those enormous amounts of fuel, you inherently need massive tanks just to hold it all. This forces traditional spaceships to basically be giant fuel silos with a tiny little capsule slapped on top. Every kilogram of fuel you add forces you to subtract a kilogram of scientific equipment or food or crew space. It's just a vicious cycle.
But early space science pioneers, like Konstantin Tsiolkovsky, realized that trying to do everything all at once was just a losing game. Their brilliant workaround was the stepping stone solution. This whole idea starts with building artificial satellites orbiting the Earth.
Now, while we usually think of satellites as being essential for weather monitoring or science research, their ultimate evolutionary role is actually as preparatory stepping stones. They're meant to evolve into permanent outposts and eventually into massive transfer stations. Imagine a cosmic harbor completely in action. We aren't just talking about a tin can floating in space. We're talking about a bustling orbital laboratory, a construction yard, and a fueling depot all rolled into one. Up there in the zero-gravity vacuum of orbit, ships are assembled piece by piece. Cargo rockets from Earth bring up the parts, the oxygen, and the fuel over multiple, totally manageable trips. The true interplanetary vessel is built right there, safely above Earth's deep gravity well. Now remember that 11.2 kilometers per second needed to escape from the ground? By departing from a transfer hub instead, that requirement absolutely plummets to just 3.1 to 3.6 kilometers per second. Because the space station is already orbiting the Earth at immense speeds, a ship leaving it only needs a fraction of the additional speed to break away completely. We drastically cut our fuel needs, which suddenly opens up vast amounts of space for the crew and all that vital science gear.
Logistically speaking, this staging process is just brilliantly intuitive. First, standard heavy-lift rockets ferry your parts, supplies, and fuel into Earth orbit. Then, specialized engineering crews assemble the deep spaceship directly at the space station. Once it's fully built, its massive tanks get topped off right there in orbit. Finally, this fully loaded, fully fueled ship departs directly for Mars or Venus. It literally turns a technical nightmare into a smooth, manageable pipeline.
And here is a totally fascinating detail that completely changes how we approach spacecraft design. No aerodynamics are needed. Because these massive interplanetary cruisers are assembled and launched in the vacuum of space, they never ever have to push through the thick air of Earth's atmosphere. They don't need sleek rocket shapes, they don't need heavy nose cones, and they don't need massive heat shields for launch. They can literally look like giant flying scaffolds built in whatever shape is actually most efficient for the crew and the machinery. So with the deep space vessel fully constructed and fueled, final preparations kick off. The astronauts, having arrived at the station in much smaller standard transport rockets, now board their magnificent ship. They step out of the transfer station, which is basically their final tether to home, and enter the craft that will become their entirely self-sustaining world for months or potentially even years. It is the ultimate jumping-off point for humanity.
And the actual departure sequence is remarkably serene. The ship effortlessly detaches and maneuvers away from the station. Because they are already up there in orbit, there is no violent, ground-shaking blast-off required to fight gravity. It is a smooth, highly calculated separation. The ship fires its engines, takes advantage of that super-low 3.1 km per second requirement, and breaks out of Earth's orbit to align perfectly with its target planet.
Which brings us to what might be the ultimate fuel-saving secret of deep space travel. Once the ship actually achieves that required speed leaving the cosmic harbor, the main engines don't even stay on for the whole trip. In fact, after just a few minutes of perfectly calculated thrust, the engines are completely shut off. For the remaining 99% of the millions of kilometers between planets, the ship simply coasts through the vacuum of space on pure momentum. Talk about an incredibly resourceful way to cross the solar system.
Of course, that peaceful journey eventually comes to an end, because beyond the harbor lies some incredibly harsh alien shores. Arriving at these destinations presents some extreme and violent challenges. At Mars, the crew has to navigate a thin, oxygen-free atmosphere, while over at Venus, they're facing a dive through incredibly dense, crushing clouds of carbon dioxide. But honestly, the cosmic harbor helps here too. Preparing everything in orbit allows us to heavily outfit these ships with the specific entry modules and heavy radiation shielding required to survive those brutal planetary conditions.
So, we've seen exactly how utilizing space stations as transfer hubs fundamentally rewrites the math and logistics of deep space travel. It bypasses that brutal gravity roadblock and gives us the ultimate launch pad. So, I really want to leave you with this lingering thought today. If space stations are our cosmic harbors, what new shores will humanity discover next? Because once we master the stepping stone, the moons of Jupiter, the rings of Saturn, and the absolute farthest reaches of our cosmic neighborhood are suddenly well within our grasp. Keep looking up.
You know when you're watching a sci-fi movie and you see these astronauts just gently, peacefully floating through the majestic silence of the cosmos? Maybe they're sipping coffee out of silver pouches, gazing wistfully at the stars. Well, do me a favor and scrub that Hollywood illusion from your brain right now. Because the actual reality of leaving our planetary cradle, it is a brutally hostile, physically punishing gauntlet. So let's dive right into this explainer, where we're going to tear away all that cinematic romance and look at the absolute extremes the human body and our engineering must survive just to make a trip to our closest cosmic neighbors.
Welcome to today's explainer. We are breaking down what we call the astronaut's gauntlet. We're going to look strictly at the raw physics of it all, the invisible terrors hiding in the void of space, and the ultimate catch-22 of actually landing. We've come through the foundational science of interplanetary travel to give you a real, unfiltered breakdown of what it actually takes to survive out there. I promise you, by the end of this, you are never going to look at a rocket launch the same way again.
Act 1. The illusion of the float, the brutal reality of weightlessness. Okay, so you might be surprised to learn that the actual thrust phase, the part where the engines are firing, makes up barely 1% of a space journey. The other 99%, you're literally just coasting. But to understand the physical toll of getting there, picture a basic spring scale. Here on Earth, before launch, everything is totally normal. You hang a 1 kilogram weight on the scale, and the dial reads exactly 1 kilogram. That's our baseline, right? That represents the normal, everyday gravitational pressure that our bones, our muscles, and our internal organs are perfectly evolved to handle. Now boom, the rockets ignite. During that incredibly violent 1% of the journey, the acceleration is absolutely crushing. That 1 kilogram weight, it suddenly registers as 4 kilograms. For the astronauts strapped in, this means they are suddenly enduring 4 to 5 times their own body weight. It's so extreme that the only way a human body can actually withstand it without vital organs totally failing is by lying completely flat on these specialized, self-adjusting couches. It is essentially a manufactured nightmare of heavy gravity.
But then, the engines cut off. We enter that long coasting phase. And that scale? It drops to absolute zero. Now, this is the terrifying reality of weightlessness. It's not just about doing fun flips in the air. It means that all mutual physical pressure between objects completely vanishes. The pressure of your feet on the floor, the pressure of your organs naturally resting against each other, it's just gone. And our bodies simply are not designed to function long-term without that baseline resistance. If we don't address it, it leads to massive physiological complications.
Act 2. Spinning for artificial gravity. Fooling the human body. So, if absolute zero gravity physically degrades us on these long-haul journeys to places like Mars or Venus, what do? We have to trick biology by creating something that isn't actually there. The solution? Massive rotating cylindrical space stations. By spinning the station, we generate centrifugal force. This force basically pushes everything inside the cylinder outwards, right against the hull. If you spin it at just the right speed, the hull pushes back against the astronaut's feet with the exact same force as Earth's gravity. It's a brilliantly clever mechanical illusion to keep our bodies from wasting away in the void. So the takeaway here is that future long-haul spacecraft aren't going to be these uniform single-gravity environments like you see in Star Trek. We're actually going to see a strict divide. You might have zero-gravity zones up in the central or upper sections, perfect for scientific experiments that need weightlessness. And then, paired with that, you'll have artificial gravity zones down in the spinning lower sections. That's where the crew will live, sleep, and exercise just to maintain their bone density and muscle mass.
Act 3. The hostile void. Invisible and physical threats in the vacuum.
Because outside the relative safety of the ship, space is not some empty, peaceful ocean. It's a lethal, high-speed shooting gallery. Think about the numbers 10 to 70. That is the estimated amount, in tons, of meteoric dust that strikes Earth's atmosphere every single day. We don't notice it down here because our thick atmosphere just burns it all up. But out in the vacuum of space, a ship traveling at immense speeds is flying completely unprotected through this invisible, relentless storm of cosmic debris.
And if you're wondering just how aggressive this dust actually is, back in 1953, the US ran this wild experiment. They sent these highly polished metal plates way up to an altitude of 140 kilometers. The total exposure to space, just 144 seconds. That's it. But when they brought those plates back down and checked them under a microscope, they found 66 microscopic impact craters. That averages out to almost 5 impacts per second per square meter. It's basically a microscopic sandblasting effect. Over a multi-year journey, that can completely chew up the outer hull of a ship, so yeah, space is incredibly abrasive.
But dust is just the small stuff, right? If you're traveling past the orbit of Mars, you face an immediate, ship-ending threat. 1,600. That's the approximate number of known, massive asteroids just lurking in the asteroid belt between Mars and Jupiter. Hitting a speck of dust degrades your hull. Hitting even a tiny fraction of one of those 1,600 massive chunks of rock? Game over. The ship would literally need sophisticated radar arrays to detect them and automatically course correct well in advance because human reflexes just aren't fast enough. And hey, if the space rocks don't catch you, the invisible killers just might. Astronauts face three major radiation threats. First, you've got ultraviolet rays from the sun, super intense, but thankfully fairly easily blocked by a standard metal hull. Second, cosmic rays. Now these are highly penetrating, intensely dangerous waves of radiation that slice right through normal metal. They demand heavy, extensive shielding. And third, ironically, it's an internal threat: nuclear radiation. Future deep space vessels are probably going to rely on atomic engines. That means the crew has to be protected by incredibly dense, specialized armor just to survive their own propulsion system. Because, nothing screams safe travels quite like armoring yourself against your own engine.
Act 4. The Perils of Landing. The ultimate interplanetary catch-22.
Okay, so you've survived the launch, the weightlessness, the sandblasting, and the radiation. You've arrived at your destination. But actually stopping? That is the most perilous part of the whole shebang. Depending on where you're going, you face two completely different, deeply terrifying landing scenarios: the atmospheric landing and the vacuum landing. One threatens to literally burn you alive, and the other threatens to leave you totally stranded without fuel.
First up, the furnace. If you are landing on a planet with a thick atmosphere, like Venus, or even coming back home to Earth, you use that air to slow down. But the friction generated by hitting dense air at cosmic speeds turns the spacecraft into a literal shooting star. The hull gets white hot. To survive this, the ship needs incredibly advanced, heat-resistant aerodynamic shielding. It is a violently turbulent descent, and it relies entirely on parachutes and the atmosphere itself to act as the brakes.
But what if you're landing on the Moon or Mercury, planets that have a vacuum, meaning absolutely no atmosphere at all, while you can't use parachutes and there's no air friction to slow you down? This is what we call the fuel trap. To stop, you literally have to turn your ship completely around and fire massive retro rockets against your direction of travel. And the paradox here is just staggering. To carry enough fuel to fire those massive retro rockets, you need a larger ship. But a larger ship is heavier. And a heavier ship requires, you guessed it, even more fuel to slow down. It's an absolute engineering nightmare of weight and mass.
So all of this really brings us to the ultimate question. We've seen the brutal reality here, from the brutal bone-crushing physics of acceleration to the bizarre degradation of weightlessness, the microscopic sandblasting of the void, and the terrifying catch-22 of finally trying to land. If space is this fundamentally violently hostile to human life and to our machines, are we truly prepared to pay the immense physical and engineering costs required to leave our planetary cradle? It's definitely something to think about the next time you look up at the night sky. Thanks so much for joining me for this explainer, and I'll see you next time.